least internal energy. So I define you internal energy in concept of real gas and ideal gas. Let's say real gas, total and internal energy depends upon two factors. First is potential energy and second is kinetic energy. Potential energy based on basically interaction between particles. And if the interaction between particles will be negative, so it will be negative. Kinetic energy based on temperature, so it will be due to temperature. Sum of these two energy will be called as internal energy. So which one of these three different states will have greatest interaction in between particles, solid, liquid, gas? You will say in solid, since they tightly packed with one another. So it will have maximum force of attraction between them. So it will have maximum potential energy. Maximum potential energy means maximum negative potential energy. So it will tend to decrease the overall internal energy of that particular system. Like in the case of gas, particles are freely moving. So it will have least interaction between them. So it will have least potential energy. So there will be very small amount of energy that will be subtracted from the kinetic energy. So it will have greater internal energy. So out of solid, liquid, gas, we can say gases will have maximum internal energy and solid will have least internal energy. Is it clear, Samira?
Yes, sir.
In first part, you have written greatest, but in second part, you have written solid will have maximum energy. How it will be possible? It must be minimum. Okay, Nara?
Yes, sir.
Next question was, which of the following is not a path function? I define using first law, dq equals to du plus dw. Du, that is change in internal energy, is state function, and rest of dq and dw is path function. So dq is equals to this. So the difference of these two energy will give you internal energy, and which will be not as path function, since it depends upon initial and final point. So your answer is correct. Third, work done. Just 1 minute. Let me show you the question. Just 1 minute. This was the assignment. Third question is related to this curve. A system goes from A to B by two different paths, as shown in the figure. Heat given to the system for path P1 is 1100 joule, and work done by the system along path 1 is greater than path 2 by 150 joule. So how much heat exchanged by the system in path 2? So for both these two different paths, we can say we have same initial and final point. So internal energy change will be same in both cases. So just write equation first law. dq equals to du plus dw, or simply dq is equals to dq minus dw. So for path first and first, it will be equals to path second and second. Now put the values as given in this question. We have for path first 1100 joule, and work done by the system along path 1 is greater than path 2 by 150. So move this work done to left side. So minus of dw1 plus dw2 equals to dq. dw1 minus dw2 is 150, which is given. So you may write 1100. If you take out minus common, so you will get dw1 minus dw2, that is 150 equals to dq2. So you'll get the value of amount of heat supplied along path 2. Nahara, is it clear?
Yes, sir.
So your answer will be, I think, 950 for this case. Good. Hatvika, any doubt? Next question is, we have three different paths, path 1, path 2, path 3, which is given in this part, for which we have to define what would be the relation between Q1, work done, and so on. So how to relate these particular curve? So let's say for all these three different paths, we have same initial and final point between A and B. Now, area under pressure versus volume curve will define you work done. So more the area it will cover, it will have more amount of work done. And since path 1 is at highest point, so it will define maximum area enclosed, then second part, then third part. And since all of them having same internal energy, so work done will be proportional to amount of heat supplied to the system. Is it clear? So option 1 will be correct. This one. Good, Nara. Next is the internal energy change in the system that has absorbed 2 kilojoule of heat and work done by the system is this much. So using first law, you may say dq equals to du plus dw. You have to calculate du. Heat supplied to the system is 2 kilojoule calorie. This particular energy is in terms of calorie. So just convert it in terms of joule by multiplying by 4.2 is equals to du. amount of work done by this particular system is 500 joule. So du will be 4.2 into 2, 8.4 into 1000, 8,400 minus 500. So I think 7900 joule. Option C will be correct. Good, Nara. Next, 110 joule of heat is added to the gas system whose internal energy is 140 joule. Then amount of external work is, so work done will be dq minus du. So 110 minus 40, that will be 70. Option B. Nara, you have used concept of, I think, chemistry. When 10 joule energy or heat is added to the system, so it will be taken as positive. And internal energy for this case is 40 joule, then how much work is done? So according to first law, dq equals to du plus dw. So dw will be equals to heat supplied to the system will be taken as positive. This internal energy on moving to left side will be negative. So you'll get 70 joule. There is difference between chemistry and physics in concept of work done. For the case of chemistry, or in chemistry, we take pressure external. That's why work done will be just negative of what we take in physics. Okay, Nara?
Yes, sir.
Using first law, or simply first law of thermodynamics in consequence of energy. Well done. That's it. Let's start. Okay, so do you have any doubt from last class to any one of you?
No, sir.
Okay, I just defined the basic concept of these three terms: internal energy, work done, and heat supplied to the system. Next, we have to start with thermodynamical process. Thermodynamical process. First is isobaric process, which is also called Charles' law. Iso means same, bar defines for pressure. So we can say the process which is carried out at constant pressure is called isobaric process. The process which is carried out at constant pressure is called isobaric process. So P will be constant. According to ideal gas equation, PV is equals to nRT. If pressure is constant, so volume and temperature will be directly proportional to each other. So we can write volume proportional to temperature. On rearranging this particular equation, you may write V1 over T1 equals to V2 over T2, equation of state for this particular process. Next, we have to calculate molar specific heat related to this process, for which we have to define generalized equation and to get the value of X. General equation is PV to the power X is equals to constant. So in this part, what should be the value of X for which P becomes constant and the component of volume part will get vanished out? Samira, any guess? The value of X for which V gets vanished out?
Zero.
Good. So if you put the value of X to be 0, V to the power 0 will be 1. So you're left with P equals to constant. That's why X will be 0. Now, introductory part, I had defined you. According to the value of X, we may find molar specific heat constant at which process? At constant pressure. So C equals to R by gamma minus 1 minus R by X minus 1. This is at constant pressure. So let's say C subscript P as Cp, or molar specific heat at constant pressure. The value of X related to this process is 0. So if you put the value of X to be 0 in this expression, minus and minus will cancel out. So you're left with gamma times R by gamma minus 1. On converting value of gamma in terms of degree of freedom, you may write 1 plus F by 2 multiplied by R. Nahara, any doubt? Okay, just write it down, all of you.
Done, sir.
Asma, done?
No, sir, I'm doing.
Asma, done?
Yes, sir, done.
Now, for this particular process, we have to plot graph to define condition or variation of different physical quantity related to this process, which is called indicator diagram or indicator curve. Indicator diagram. So for any process, we mainly have 6 different types of curve, 3 for expansion and 3 for compression. I will define only expansion part. If you reverse the direction of that arrow related to any curve, you will get compression curve as well. So first is pressure versus volume. This is pressure versus volume, pressure versus temperature, volume versus temperature. Since pressure is constant, so graph related to this PV curve will be straight line parallel to opposite coordinate. Since pressure is constant, so it will be straight line from this point to this point, and arrow will be along this direction from some initial value Vi to some final value Vf. In second part, since pressure is constant, so only temperature will change with change in volume. So curve will be along this from some initial value to some final value. And for third part, since volume and temperature is directly proportional to each other, so curve related to this part will be straight line like this. For some other value, some other straight line like this. So related to this part, you will be asked which one of these two curves will have higher pressure. So let me define you how to solve. Just write ideal gas equation. PV is equals to nRT. Since this particular curve is representing volume and temperature, so keep volume and temperature to one side and rest of the quantity to another side. So you may write volume divided by temperature equals to nR divided by P. This quantity, volume divided by temperature, is also called perpendicular by base related to this curve. We may write this perpendicular by base ratio as slope. In right side, we have n number of moles, which is constant, R universal gas constant, which is again constant. So we're left with just pressure. So we can say slope of this particular graph is inversely proportional to pressure. So more the slope of curve of volume versus temperature, it will have lesser amount of pressure. So let's say this is A and this is B. Atvika, just tell me which of these two curves having more amount of slope or having greater slope? A or B? Slope simply defines you the inclination part. So you can say A is inclined at greater angle as compared to B. So slope of A is greater as compared to B. And since slope is inversely proportional to pressure, so we can say pressure at B is greater as compared to A. Is it clear?
Yes, sir.
Asma, any doubt?
No, sir, no doubt.
Okay. Now, related to this curve, we have to mainly define for PV curve, we have to calculate some of the quantity. First is slope of pressure versus volume graph. Since this PV curve is a straight line parallel to x-axis, so you will say inclination of this particular line with respect to x-axis is 0. So tan 0 will be 0. So we can say dp divided by dv, which is equals to tan theta, it will be 0. Now, related to this slope, we have to define bulk modulus. You must have learned in chapter mechanical properties of solid, in which I define you bulk modulus equals to volumetric stress divided by volumetric strain. Volumetric divided by volumetric strain. Volumetric stress is perpendicular force acting over area, which is also termed as pressure or simply change in pressure, divided by volumetric strain, change in volume by original volume with some negative sign. So we may write delta P by delta V as dP by dV for instantaneous part with some negative value multiplied by volume. So I'm using this equation for this part. Beta equals to dP by dV multiplied by volume. And since dP by dV for this curve is 0, so you'll say beta for this process will be 0. Okay, just write it down till this.
Done, sir.
Asma, done?
Yes, sir, done.
Now, next thing we have to calculate related to this curve is work done. Work done is simply area under pressure versus volume graph. So in this part, pressure is constant and volume is changing from some initial value to some final volume. So it will be V final minus V initial. You may convert this expression PV is equals to nRT. So it will be nR at some final temperature minus initial temperature. So using the above part or below expression, you may get the value of work done related to the expression given in the question. Next, since this process is isobaric process, so for which we have to calculate heat supplied or ejected. So dq equals to number of moles times C times dt. For this part, which is isobaric process, so C will be Cp. So N times Cp is gamma times R by gamma minus 1 times dt. You may convert this particular formula in terms of degree of freedom as well, or just keep it as it is. Third, internal energy we have to define and relationship between those three different quantity. In last to last class, I defined you how to calculate internal energy as du is equals to n times r by gamma minus 1 times dt. And for this part, we have dq equals to n times gamma r dt divided by gamma minus 1. So just divide these two expressions. Rest of the all quantity will get cancelled out. So you're left with dq du will be 1 by gamma, or you will say dq equals to gamma times du. So I'm defining a generalized relation between these three different quantity. dq equals to gamma times du, which is equals to gamma divided by gamma minus 1 dw. So if you know any one of the quantity related to this, you'll be able to calculate the rest of the two quantity by using this expression. Nahara, is it clear?
Yes, sir.
Okay, just write it down. Then I'm giving you some problem related to this part.
Done, sir.
Done, sir.
For helium, indicator diagram is given as pressure versus volume. Let's say this is A, B, 2 atm, 20 centimeter cube, 50 centimeter cube. If temperature at A is 27 degrees Celsius, find first temperature at point B, second work done during this process, third heat supplied. Let me give you a hint how to calculate these quantity related to this question. For first part, you may write, or let me give you some conversion relation. 1 atm equals to 10 to the power 5 Pascal. 1 centimeter cube will be 10 to the power minus 6 meter cube. So for first part, I have temperature at point A, which is 27 degrees Celsius. So convert it into Kelvin first. So you may write temperature at point A is 273 plus 27, that is 300 Kelvin. Now we have to calculate temperature at point B. This whole process is isobaric process, that is pressure should be constant. So at constant pressure, volume and temperature is directly proportional to each other. So we can write equation of state related to this process as V1 by T1 equals to V2 by T2. Just use this expression and try to find temperature for point B. Next, for work done is area under the graph. So use the above formula, you will get amount of work done. And for third part, use this expression which I have derived, relation between these three quantity, you will get amount of heat supplied to the system. Try to solve related to this given term according to the question. Yes, Shravya. Good, Samara. Good, Shravya. Good, Shravya. Good, Samira. Let me solve with the first part of this. At point A, we have volume 20 centimeter cube. So you may write 20 into 10 to the power minus 6. Divide by temperature at point A is 300 Kelvin equals to volume at point B 50 centimeter cube. So 10 to the power minus 6. Divide by temperature at point B, we have to calculate. Akifa, is it clear?
Yes, sir.
Now, just move this TB to left side. So it will move to numerator and rest of the quantity to right side. So you'll get TB equals to 15 to 10 to the power minus 6 multiplied by 300 divided by 20 into 10 to the power minus 6. So 10 to the power minus 6, 10 to the power minus 6 will cancel out. 0, 0 will cancel out. So 3 into 5, 15 divided by 2. So it will be 750 Kelvin. Asma, is it clear?
Yes, sir, it's clear.
Okay. Next, we have to calculate work done. Work done is area under the graph. So work equals to pressure volume final minus volume initial. Akifa, just tell me the value of pressure related to this process. How much it is given in the question? 2 atm. Okay.
Okay.
So 2 atm, 1 atm equals to 10 to the power 5 Pascal. So just multiply it by 10 to the power 5. Volume final, that is volume at point B, we have 50 minus volume at point A, 20. In terms of centimeter cube, so just multiply it by 10 to the power minus 6 to convert into SI unit. Now simplify it. 2 into 50 minus 20, 30 into 10 to the power plus 5 and 10 to the power minus 6. So plus 5 minus 6, it will be 10 to the power minus 1. So 2 into 30, 60 into 10 to the power minus 1. So you may write 60. 10 to the power minus 1 will be written as 1 by 10. So this 0 and this 0 will cancel out. So you'll get just 6 joule. Nahara, is it clear?
Yes, sir.
Okay. Now just tell me about this particular gas. We have this particular entire process for helium. Whether helium will be monoatomic, diatomic, triatomic, or something different.
It will be monoatomic.
Good. So what will be the value of degree of freedom for monoatomic? Degree of freedom for monoatomic gases? Asma, if you know. Arpika, the value of degree of freedom for monoatomic gas? Just look. How much it is it? 3. Okay. So for monoatomic, degree of freedom is 3. So we may calculate gamma as 1 plus 2 by F. Good, Asma. So F is 3. So on rearranging, you'll get 5 by 3. Now use the expression dq equals to gamma divided by gamma minus 1 times dw. Put the value of all term and simplify it to get amount of heat supplied to the system. Try to solve. Shravya, just put the value of work done to be 6 joule and simplify it. Good, Samaira. Good, Shravya. Just see, we have gamma equals to 5 by 3. Divide by 5 by 3 minus 1 multiplied by work done 6. So in denominator of this 1, there will be nothing but 1. So take LCM to be 3. So 5 minus 3 divided by 3, that will be 2 by 3. So on simplifying, you will get 5 by 3 in the numerator, divide by 2 by 3 in denominator, multiplied by 6. So 3 and 3 will cancel out. So you're left with 5 by 2 multiplied by 6. So 5 into 6, 30, divided by 2, 15 joule. Now we have heat supplied to the system and we have calculated work done. So according to first law, you will be able to calculate change in internal energy. So dq equals to du plus dw. So du equals to dq minus dw. dq we have 15 and dw 6. So 15 minus 6, that will be 9 joule. Samaira, is it clear?
Yes, sir.
Asma, any doubt?
No, sir, no doubt.
Okay. Asma, written?
Yes, sir, written.
Okay. So this is all about isobaric process or process at constant pressure. Next is isochoric, which is also called isometric process. Or Gay-Lussac's law. The process which is carried out at constant volume is called isochoric or isometric process. the process which is carried out at constant volume is called isochoric. So volume is constant. According to ideal gas equation, PV equals to nRT. So if volume is constant, so pressure and temperature related directly proportional to each other. So we can write pressure directly proportional to temperature. So P1 divided by T1 will be equals to P2 divided by T2. This will be termed as equation of state related to this process. Now we have to calculate the value of X. So let me write generalized equation P to the power 1 by X, V equals to constant. So what should be the value of X so that this pressure part will get vanished and you will left with volume equals to constant. Just think what should be the value of X related to this expression. Sumaira, any guess?
0.
1 by 0 becomes infinite. So pressure will be dominant in that case as compared to volume. Okay.
Okay, sir.
So it should be reciprocal of 0. What is called reciprocal of 0? Infinity. So if you put the value of X to be infinity, 1 by infinity becomes 0. So P to the power 0 will become 1. So only you're left with V equals to constant. That's why X will be infinite in this case. So on the basis of X, let me define you molar specific heat at constant volume. So C equals to R by gamma minus 1 minus R by X minus 1. Put the value of X to be infinity. So infinity minus 1 will be again infinity. Any number divided by infinity or simply 1 by infinity will be 0. So this entire term will become 0. So you're left with R by gamma minus 1. If you convert this gamma in terms of degree of freedom, you'll get F by 2 times R. And since this is process at constant volume, so it will be termed as CV. Shravya, is it clear?
Yes, sir.
Now, related to this process, since we have constant volume, let me define you indicator diagram. Pressure versus volume versus temperature, and pressure versus temperature. First, pressure versus volume. Since volume is constant, the graph will be parallel to opposite coordinate like this, along this direction. In second part, volume is constant, So graph will be a straight line parallel to opposite coordinate. Third part, pressure versus temperature. Since pressure and temperature related to this process is directly proportional to each other, so graph will be a straight line. Let's say this is A and this is B. So let me define you what its slope would signify. So just write ideal gas equation. PV is equals to nRT. Since this graph is related with pressure and temperature, so move pressure and temperature to one side. So pressure divided by temperature equals to nR divided by volume. This particular quantity is related to this curve will define your slope, and it should be proportional to 1 by V. It means greater the slope of pressure versus temperature, it will have smaller volume. So related to this graph, you can say B having higher inclination, so it will have more slope as compared to A. So volume of A will be greater as compared to volume of B. Asma, any doubt?
No doubt, sir.
Okay, just write it down, all of you.
Done, sir.
Done, sir.
Done, sir.
Nahara, done?
Yes, sir.
Okay. Now related to this part, for PV curve, we have to calculate first slope of pressure versus volume graph. Since this line is inclined at 90 degrees with respect to x-axis, so slope dp by dv will be tan theta, and tan 90 will be infinite. So dp by dv for this process will be infinity. Now related to this quantity, we may define bulk modulus. Beta equals to minus of dp by dv multiplied by volume. Since dp by dv is infinite, so this entire term will be infinity. In mechanical properties of solids, I defined you if modulus of elasticity of a particular material is infinite, it means the body will behave as perfectly rigid. Since in this part, bulk modulus is coming out to be infinity, so we can say this process will behave as defined for perfectly rigid system. Samaira, any doubt?
No, sir.
Next, we have to calculate work done. Since in this part, there is no change in volume, so there will be no compression or expansion of gas related to this part. So work done in this process will be 0. So according to first law, we can say dq equals to du plus dw. dw is 0 in this part, so du equals to dq, which should be equals to n times c dt, and c in this process will be cv, that at constant pressure. So this will be an expression for this part. Okay, just write it down.
Done, sir.
Done, sir.
Akifa, any doubt?
No, sir.
Okay. Asma, written?
Yes, sir, I've written.
Okay. Now, related to this process, you will be asked some conceptual question like, why tires of vehicle on long drive got burst? Any idea? You must heard about it, especially in India. Let me define you the process behind it. You'll say there will be friction between tires of vehicle and road on which it is traveling. That friction will causes some production of heat, which leads to increased temperature of gas inside that tire. And since volume of that tire will be constant, so at constant volume, pressure and temperature should be directly proportional to each other. So increasing temperature will lead to increase in pressure of tire from inside, and that will be responsible for bursting of tire for long driving. Is it clear?
Yes, sir.
Yes, sir.
So you'll say due to friction, between road and tire, which leads to increase temperature of gas inside it, and at constant volume, pressure is directly proportional to temperature. Hence, pressure increases which causes the get bursting of tire. Asma, any doubt?
No, sir, no doubt.
Let me define you another physical phenomena. Suppose take any ice block placed over any support, let's say placed over any support, this is ice block. Now, take any wire, place it horizontally at this point, and attach some mass to it at both ends. So what will happen to this particular whole system? You will observe there will be movement of this string downward. So what process will be in this part? This whole term, you'll say there will be no change in volume just beside this string. So you'll say volume will be constant. So at constant volume, pressure and temperature directly proportional to each other. So these small block provided at its end, this and this, will be responsible to increase pressure of this particular string over this ice block. So on increasing pressure, temperature just beside it or just behind it increases, which will lead to change in state of ice from ice to water. So there will be some melting process just behind it. Is it clear?
Yes, sir.
Yes, sir.
Now, due to melting of ice, this string or this particular metallic strip may go downward. So at some point, it may reach to this, and may get completely eject out from the other end. On the other hand, on moving this particular string downward, liquid at its upper portion will remain or again return back state and back converted into ice due to temperature of its surrounding. So there will be some refreezing of water present over it into ice. So again, ice will form just above it and it get completely passed on from the other side. This whole process is called regeneration. Regelation. Is it clear what is
Yes, sir.
happening here? Samira?
Yes, sir, clear.
Okay. Just write it down to this. This entire process is called regelation.
Done, sir.
Aisha, any doubt?
No, sir.
Asma, done?
Done, sir.
Done, sir.
Now, next question will be asked about Mayer's relation, or simply relation between Cp and Cv, or why Cp is greater than Cv. So let me define you this entire term and explain you why Cp is greater than Cv. Suppose this is any system in which piston is free to move In second part, let's say piston is fixed. So what will happen if you supply heat to this system and to this system? In the right side, we can say since piston is kept fixed, so volume of gas will not change. So you will say at constant volume, amount of heat supplied to the system would be utilized only in changing internal energy, since work done in this case will be 0. So if you are supplying 10 joule of energy to this particular system, this 10 joule entirely will get converted into internal energy. But in left part, suppose at constant pressure, if you supply dq, it will convert into du plus dw both. So in this part, if you have supplied 10 joule to this particular system, some of energy will convert it into internal energy and some in terms of work done. Not the whole part would get converted only in terms of internal energy. So if you have to check, or if you have to get same amount of internal energy for both these two processes, you must have to increase the amount of heat supplied to the system. Let's say you have increased to this particular heat by 15 joule. So for this part, it will become 10 joule and let's say 5 joule. So to get the same amount of internal energy for both these two processes, we can say amount of heat required at constant pressure will be greater as compared to constant volume. Since at constant pressure, some of energy may be converted in terms of work done as well. That's why we would require some extra amount of work or some extra amount of heat supplied to the system at constant pressure as compared to at constant volume. Hence, Cp, that is molar specific heat at constant pressure, should be always greater than molar specific heat at constant volume. Samira, is it clear?
Yes, sir, clear.
Akifa?
So could you explain this again?
Okay. In right hand side, I'm taking constant volume. So if you supply heat to this particular system, this entire heat will get converted into internal energy since there will be no any work done, since volume is constant. So if you have applied 10 joule, this entire 10 joule will convert it into internal energy. But at constant pressure, if you apply 10 joule, some of energy may convert it into internal energy, and some in work done. So if you have to get same amount of internal energy change for both these two processes, you must have to increase the amount of heat supplied to the system since some of energy is converting into work done as well. So I've just supplied 15 joule. In this part, I got 10 joule change in internal energy and 5 joule for work done. Now just compare internal energy for both these two processes. Having same internal energy, so to get same amount of internal energy for both these two processes, you must have to supply some extra amount of heat at constant pressure as compared to constant volume. Is it clear?
Yes, sir, it's clear.
So you can say at constant volume, amount of heat supplied to system is utilized in changing internal energy only, but at constant pressure, amount of heat supplied is utilized in changing internal energy and work both. So to get same amount of internal energy, at constant pressure, more amount of heat would be required. Hence, Cp is greater than Cv. Let me derive this particular part mathematically. First, write it down.
Done, sir.
Done, sir.
Hatvika, any doubt? Asma, done?
Yes.
Okay. So let me define you this particular entire relationship mathematically. At constant volume, dq equals to du and should be equals to n times cv dt. Let's say this is equation first. At constant pressure, dq equals to du plus dw. dq is heat supplied to the system at this process, so it will be n c at constant pressure times dt. du we have calculated above as n times cv dt. Work done is pdv. Now, let me convert this PV in terms of some temperature. So you can say, using ideal gas equation, PV is equals to nRT. Since in this part, we have constant pressure. So just differentiate this entire term using temperature. So you'll say, differentiating with respect to temperature. So P is constant, keep it outside. Volume dV by dt. N into R is constant, keep it outside. Differentiation of temperature will be 1. So on rearranging, you will get PdV equals to nR times dt. Now put this value of PdV in the above expression. So you'll get n times Cp dt equals to n times Cv dt. PdV we can write nR dt. ndt will cancel out from either side. So you're left with Cp is equals to Cv plus R, or move this Cv to left side. So you'll get Cp minus Cv is equals to R. This is called Meier's relation. Nahara, is it clear?
Yes, sir.
Aisha, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Done, sir.
You all have done?
Yes, sir.
Asma? You have written? Okay. So this is all about isochoric process. We have just finished it. Let's stop here for today. I have to take viva of some of the student. Okay. So you may leave the rest of them. Asma, Aisha,